Hey folks, welcome to session 7 of High Performance LLMs from First Principles. So our goal again, how to achieve high performance for LLMs. And we kind of have two main topics this week. We're going to finish the end-to-end training performance conversation. So we're going to just review the math on it, then make sure we're actually getting good performance. Secondly, we're going to discuss inference performance. So we're going to figure out the math behind inference performance, and we won't have a chance to code that today though. Cool. So just remember program, predict, profile. So a mix of those three things today for sure. And let's just start by asking this question, like how long should training take? So we put together a full training loop last time, but we never figured out how long it should take. So training is the forwards pass and the backwards pass. And we're going to start just by counting through the forwards pass. And just a reminder, hop in with questions anytime. The question's super, super helpful for me. See how I'm doing. So if we remember the forwards pass, we're just multiplying a matrix on the left, which is usually called the activations, batch by E1, by weights, E1 by E2, and we get something of batch by E2, which is the next layer's activations. So the number of flops is going to be 2 times batch times E1 times E2. And that's just because the fact we've learned about matrix multiplies is the product of 2 times the product of the 3 dimensions is the number of flops in a matrix multiply. And then conveniently, E1 times E2 is the number of parameters in the matrix multiply, right? Because it's the number of learnable parameters. So you get this really handy way of thinking about these things, which is the matrix multiplies take 2 times the batch and tokens times the number of parameters. So it's always how many flops we say there are in the forwards pass, ignoring attention in a transformer. Cool. So the backwards pass is actually a little bit trickier, and I don't really want to go through all the steps in back propagation. It's a little bit funny, but these are the 2 matrix multiplies that occur in the backwards pass corresponding to the 1 matrix multiply in the forwards pass. The first one is a partial derivative. So we have a partial derivative with respect to layer I plus 1. We multiply through the transpose weights and get a partial derivative for the next layer. And the second one is we take the derivatives for this particular activation layer, the partial derivatives, and get the derivative with respect to this layer. So these are the 2 separate things we have to do in the backwards pass that Jack's actually doing for us automatically. And they both take 2 times batch times E1 times E2 flops. So the whole thing just simplifies to the 6 times batch and tokens times parameters flops. So this is a really, really important rule of thumb for training. 6 times batch times parameters. And it all comes, again, just to summarize it, it all comes because this is the number of parameters. So the number of flops is 2 times batch times the number of parameters. And then there are 3 matrix multiplies instead of just 1. Any questions here before we dive into making this into code?
So I have a question. Sorry for my voice. I have sore throat.
Of course.
So you have the B here, but B is just the artifact of how we divide data. It could be just a number of like size of training data set or something like this instead.
Yeah, it's the number, exactly. It's the number of training tokens we're doing during this step, during this train step. So it's the number of words or tokens we see in the training set.
I would multiply it by the outer loop count somehow.
Okay, yeah, exactly. That's a really, really good topic. So a very common thing to do is someone will want to train like a 1 billion parameter model for 20 billion tokens. So here I'm really counting the number of flops in a single step. So a 1 billion parameter model times 20 billion tokens, and then multiplied by 6. You just multiply those, and that's how many flops there would be in that whole training loop. So that's a very, very useful quantity as well. Does that answer the question?
Yes, thank you.
Awesome. Cool. So we're going to go to coding. I have given myself some handy dandy cheating hints here, just because I just did this right beforehand. Would love to make sure I get it right. So what do we have to do? So the first thing we have to do is count the number of parameters. Then we're going to want to calculate flops, which, as we learned, is 6 times batch times parameters. Then we'll see if that works or not. And then I have written myself a note, this lacks sharding constraint, to help us get just maybe a little bit better performance. So let's just go through it step by step. Cool. I know I always have my screen too small. Hopefully this is okay for folks. Just speak up if this is still a problem. So this is exactly where we left the code at the end of last week. So this is and basically what we've done is we've defined our train step. We have defined the dynamics. We have our data loop, and then we are doing this. So the key kind of thing we have to do is count the number of parameters we have in the model. And JAX is all about this concept called a pie tree. So parameters is a pie tree. So the way we're going to count the parameters, so calculate parameters, is for like an arbitrary pie tree. JAX has some useful things. So the first one is dax.treeutil.treemap. And we can do lambda x to x dot size, I believe. And we can map that over the pie tree. So that will count for us how many parameters there are in this pie tree. But it will be each of these leaves. I guess I should probably just throw in a breakpoint. We can just maybe take a look at it all together. So let's just, I'll put that in here. Cool. So, and by pie tree, it's a very fancy term. It's just a nested list of dictionaries and arrays. That's all Jackson means by that. Uh-oh. Looks like I accidentally made some changes. Let me just quickly. Yep, I accidentally made some changes to this file. I'm sorry about this, folks. I'm just going to check this out to make it clean. Okay, so we will put a breakpoint in here, and we'll get started again. So all this is saying, all JAX is doing in a pie tree is a nested list of these arrays. So all we have to do to count it. So if we look at params now, we can see params is just a bunch of arrays. So if we look params, it's a dictionary, and then it has within it more dictionaries. So each of these leaves is actually just a JAX array. So the easiest way to count them is actually jax.treeutil.treemap, and we can do lambda x to x dot size. We can do whatever we want, but I'll do x dot shape first for params. And this is now giving us, it's mapped over all of the leaves. So that means all of the arrays in this dictionary, and it's given us a shape. We actually wanted a size, so I'll do x dot size, and now it will have counted all of the parameters in each of these keys. So as we're writing calculate num-parameters for an input pie tree, this is actually the first thing we're going to want. So we're going to be sizes equals dax.treemap.treeutil. treeutil.treemap. And then this is a very simple lambda x to x dot size over a pie tree. Perfect. Now we have to figure out how to sum this. And again, all of these things, you don't need to use the JAX tools, but they are kind of nice. So probably the easiest one here is we just want a tree reduce. So we'll run this line of code, and then we'll do a tree reduce. So we'll do a summation over the leaves. So here we have sizes on params, and then we will do jax.treeutil.treereduce lambda x y x plus y over sizes, and that can be total size. Okay, so that is just summing it up. So again, the reason these things are in JAX is because it's just so incredibly common in JAX programming to need these functions. So here we are. So that will calculate the number of parameters. And now we can just calculate our parameters. Number total params is calculate number of params and underscore params. Okay, perfect. So now it's the total number of flops. Well, we said it was 6 times batch times parameters. And we just have to count the batch really carefully. So the batch is actually going to be the batch in sequence times the sequence length. So recall that right, because before we were counting the batch and tokens. So the number of tokens is batch and sequences times sequence length. Hopefully I get an autocomplete here. Perfect. So that's the total number of tokens we're processing times the number of parameters, and then times 6 based on that formula we already calculated. And we can just print the total number of flops, and that can put us in good shape here. Perfect. So the next step we're going to do is try to calculate our model flop utilization, because now that we know how many flops of work we're doing, we know how much time it's taking, we can directly calculate our model flop utilization. Before we jump into that, any questions here? Cool. So, what do we really want to calculate? So probably it'd be better, instead of having calculating the total number of flops, to have a total number of flops per device, right? And that's going to be the total number of flops divided by the devices, and then actually look at this, that'd be a device count. And then if we want to calculate the calculate our flops per second, we have to calculate how many flops of work we've done and divide that by the time that's elapsed. So last time for we were a little hacky. We put a constant there. I'm just going to call it log period. Okay, and then our per device flops will be, so the per device flops completed in interval will be our per device total number of flops per devices times our log period, because that's how much work we did. And I'm going to just put that into teraflops, just so we can actually read the number that comes out. Okay, and then we'll get our T flops per second per device is our total flops completed in an interval divided by our time elapsed in seconds. That is correct. Cool. And we can run this, and now this should be printing out for us how many teraflops per second we're achieving per device from the code we wrote last week. So you can see we are at 6. So let's take a second. Is 6 good or bad? And I guess it's always hard to remember. I'm just going to pull up a system diagram. And we are getting 6 teraflops per second. And this the compute is supposed to be able to give us 275 teraflops per second. So we're getting literally 6 out of 275. And that's about 2% model flop utilization. So we aren't doing great. I did go through this exercise, so I've written myself notes. So we're now down to XProf. Cool. So I'm going to open up this XProf. Can folks see okay? Hopefully. And one of the keys to getting best performance is always to be able to profile. So here we have kind of profiles up. And we can see our time is actually taken up in a fairly regular thing where we're doing this fusion operation. And if we look at this fusion operation, I think if we zoom in on it, we can try to see what's happening. It's actually all reducing something that's the shape of our activations. So this is a 384 by 256, which are within our sequence length, within our vocab, by 8192. And that's being all reduced, which means being averaged across all of the chips. So that's not the communication pattern we're expecting to see here. It's like a XLA. We haven't told XLA how to solve this problem, so XLA is going to do its best job. Unfortunately, that best job isn't very good in this particular setting. So with a little hint, we can do better. Before we get, let me just hold. Any questions about where we are
Rafi,
here?
could you go back to the profiler for a second
Yeah.
and what led you to suspect that that was the step that was the one that we should investigate?
Okay, so let me just, that's super helpful. Thank you for that question. So each of these things are JIT steps. So I've timed here like 9 of them or whatever. So I'm just looking within one of them. And I see this highly regular structure. So each of these fusions looks the same to me. So I'm looking within each of the fusions. And what I can see is this fusion is saying it's doing an all reduce. And then based on the size of the all reduce, it's quite large all reduce. And that's what's leading me to believe that the compiler, there are a lot of the compilers chosen a bad strategy for solving this problem. One other thing that maybe I should highlight also before I is like this is actually the actual arithmetic that's happening here, and this whole thing is just communication because it sounded we were very communication bound in this profile.
Got it. Thank you.
Good question. Any more questions? So the kind of like magic here.
Rafi, one question.
Yeah, absolutely.
Can you look at that profile and see that 2% there? Like, is that visible in that profile picture if you sort of squint at it hard enough?
It's not quite visible. So there are a lot of related facts that are visible. So maybe I'll show you one of them. But it's not quite. So this is telling us that we're spending 11% of our time. So I went to HLO up profile if you're doing this on your own. And it's telling us that we're doing 11% of our time in convolution fusions. And we're achieving 64% utilization. So if you multiply that through, that'd be like 7%. So the compiler is telling you that it thinks it's achieving 7% T-flops utilization. Well, my calculations are showing we're only doing 2. And the reason for that is because this compiler can insert additional flops. So what it really means by this is that the MXU, the chip is busy. 7.7% of the work, huh? But it's actually hard in the profiler to see how long the work should take. So typically we encourage you to have analytical models for how long the work should take to complement the data they see from the MXU. And you should always be getting less throughput than this because, of course, just because the chip is working doesn't mean it's doing useful work.
Cool, thanks.
Great question. Any more questions? Cool. So the way we've seen this a little bit earlier on, and the way we're supposed to deal with this is by basically giving a hint to the compiler. Hey, here's how I want you to shard these things. So we have all of this math that we've written out a little crudely here, and the compiler understands. We've told the compiler, hey, multiply X by this matrix, or do this round. All of these things we've told the compiler how to do, but we haven't told the compiler detailed instructions of how to do it. So the next level of detail, there are a couple more levels of details we could go to if we need to, but the simplest level of detail is to just tell the compiler, hey, here's how I want this sharded. So the way I'm going to do that here is I'm going to put a sharding constraint, telling the compiler as it operates, here's how to leave certain sharding. So just for convenience sake, I'm going to move this mesh a little bit higher. Cool. And then we're going to make the sharding constraint we want. So this is like desired embedding sharding. And that's jax.sharding.name sharding mesh. And then jax.sharding dot partition spec. And recall that the way we're going to apply this to things that are batch sequence embed. So that means that based on the rules we've identified in our language, we call this FSDP, none, and tensor parallelism. And now all we're doing when we are all the hints we're giving the compiler to help it get better performance is in the various places. We're just saying JAX, like x equals x JAX dot locks dot with sharding constraint. So this is just like a pass-through constraint, x, and then this object whose name I forget, named sharding embedding. And literally, we just have to sprinkle this in. Actually, we could think about how often we really have to, but it's free. It's just an annotation that gets compiled out, so we can just throw a few of them in wherever we want. I'm just going to see if there are any more that I can find here. If we put one at the bottom, it shouldn't matter too much. Cool. And then we can multiply through. And we'll see what type of performance we get now. This should give us a little performance boost. Cool. So now we're up to 46. So just to remind us where we were earlier, we were at 2, which was not good. Now we're at 46. So 46 is over 275, 16%. So that's actually a lot better than 2%. I think the other thing we're doing that's a little bit hurting ourselves here is our matrix dimensions are so small. So this is a 512 by 1024, So all these things are just pretty small. I'm going to just make these a little bit bigger and see if we get to a better model flop utilization. The trade-off here is that everything will run compile a lot more slowly. There are additional optimizations to make the compiles faster. I'm going to add a couple more layers too. So this is going to be a lot slower. So just making basically the model is so small. I believe that the small size of the model is hurting us. So hopefully slightly bigger will help here. And then there are additional optimizations to make the compile faster. But again, just because we're in a little bit of interactive environment here, it's good to have a fast configuration. And the work to speed up the compiler. The compile is just a little bit slow. So I think I'll spare us here. So hopefully we'll get reasonably good performance here. And then we can be reasonably happy. And we'll move on to inference. So maybe while we're waiting here, I'll just tell people about the compile optimization that we haven't shown, which is right now we're actually doing what's called unrolling the loops. So this is a for loop in Python. But when XLA sees this, all of that structure has been removed. It no longer knows that these are all within the same, all of the loop bodies are the same. And it's really making 8 separate compilations through this process. So in like the bigger code bases, you'll see that we do what's called a scan, where we stage this for loop carefully. So JAX is able to identify that these are all the same. And then that allows a much faster compile time. So compile time that's linearly faster in layers. Luckily, we now have performance data. So 195.5 teraflops per second per device. And if we just do the math, 195.5 over 275, 71%, which is actually quite good. So good performance on single host here. We've made it a pretty easy neural net, but still good to see performance reasonably close to the physical limit too.
Rafi, could you show us this in the profiler to see if it appears different?
Yeah, let me do that next week. I'll take an action item there. Okay. Better profile. It actually is going to look just like what you're used to from the times we've done it. The times we've done it for like other workloads. Like it looks just like that MATLAB workload actually. But super good question. I'll definitely pull it up. I just don't want to go through the shenanigans right now, actually. Cool. Cool. Any questions about training, Chetna?
Hey, Rafi, so you showed the example for one host. If we were to scale it to like thousands of hosts, um, I mean, how does the sharding strategy that we just looked at scale?
Yeah, it's a really, really deep and important question. So the sharding strategy so assuming that they're all within the same interchip interconnect, which nowadays on V5P goes to like 2,000 or so, depending on the pod. This same strategy would work, and everything would work exactly the way you expect, as long as you keep growing the size of the problem. So here we were working on, like, I think well, let's do the math together. Actually, excuse me. Here we were working on 384 by 128, right? 384 times 128 over 4, 10,000, 12,000 tokens per chip. And this whole strategy is going to work great as long as you give every chip 12,000 tokens. One of the main scalability concerns, Chetna, is if you have like 8,000 chips and you give each chip 12,000 tokens, the model might not learn as quickly, so that you end up hitting constraints that are separate from what we've discussed here. So you hit a constraint on the global batch size. How many total tokens you're willing to use in one training step ends up being one active constraint. And that drives you into the more complex strategies, including tensor parallelism. That we actually also could do in here. Maybe I should just show that too, actually, while we're here. Does that answer the question? So there are reasons we outgrow this strategy, but they are more complex.
Thank you.
And you expect almost the same performance if you go to thousands of chips. And actually, almost the same code will work. So to switch to tensor parallelism, we would just do this. And then if you think about it, we should be significantly slower here, because one of the rules we identified is that the feed forward dimension has to be at least 4 times 2048 to get reasonable performance. So this is going to be kind of on the regime with tensor parallelism, where we just get like not good performance or not like truly terrible performance. That was kind of a previous session on sharding, so we worked that out. So I'll run this with tensor parallelism. Cool. More questions. Love it. Great.
Yeah, Rafi. So I have a question about the X-proof. So when we see the trace view for that profile, how we usually map back to our source code? The reason I ask that is when sometimes when I see those profile, I don't know which operation we should actually optimize. So could you provide some suggestions?
It's actually can be a little bit trickier than you would like it to be. So some of them will directly map back to the source code. Interesting. None of them are doing that for me right this exact second. But some of them, when you hover over the line number, it will directly map back. So the most helpful way of doing it is Jack's named scopes. So I'll just show that here. So you can provide annotations. So I'll just quickly show this here. You can put annotations into your code, and then those annotations will show up in the profiler. So those annotations allow you to understand what's going on, and then combined with seeing the sizes of the operation, and then sometimes, depending on how much optimizing has been done, the compiler is able to trace this back to a line number. That's kind of usually the best mix.
Okay, thank you.
But named scope super powerful. So you can just see it like kind of the invocation here, where different things get assigned different names.
Okay, thank you.
Great question, Ryan. Any more questions here? Cool. Let's see if tensor parallelism compiled. Okay, so we're getting 24.7 teraflops per chip, which is not, again, showing us that in this regime, tensor parallelism is wrong. Cool. So unless there are any more questions, I'm just going to jump through the math of inference, explaining what's going on when we think about inference. And then I think that'll be it today. Cool. So reminding ourselves like when the world is going on here, the way the neural net is doing things, it's like this causal or ordered autoregressive model. So autoregressive means it needs to see the prior inputs to decide the next outputs, and causal means that it's left to right, right? So to know what it will say for and, it needs to also know so long, but it doesn't need to know thinks to do and, right? So that's causal and autoregressive. So what we're doing here is we have an input, so long and thanks for, and we need the neural net to output all the fish. And one of the really kind of important things, we've talked about it a number of times, is when we see the input so long and thanks for, like where do we actually use that information during next token generation? So like how do these tokens fit? And the answer is only in attention. Everything else, so it's really the neural net is basically its attention and feed forward layers. Only attention depends on the previous results. So during inference, what we need for attention is usually called the KV cache or key value cache. And it's this representation, so it's batch by previous tokens, by number of heads, by head dimension, for the keys and the values that feeds into feeds into the attention. So the query comes from the new token, but the batch, the previous token, the number of heads, and the head dimension all come from the previous token. And then the other thing that's really important is the neural net, when it reads so long and thanks for, it can read that all at once. But when it starts doing all the fish, it needs to choose the tokens one at a time. So it needs to do one pass for each of the generate steps. So to break this out really like precisely a little bit more in terms of math, we have so long and thanks for. We need to output all the fish. The first step is we do a prefill, which is so long and thanks for, and it suggests the next token all. Then we put all to the next token, right to the KV cache, and it should output the. And so the computation, one serving request for inference is one prefill, and it's actually n generates. Each of them give us one output per token. So that's to service like one customer request, like one request with Gemini or ChatGPT, n generates one for each output token, and the prefills, so all of your prompt, everything you write, can go through in one pass through the neural net altogether. So it's really, really important, this idea that the decision making for the next token depend on what decision was made for the current token. And how long is generate going to take? Well, the feed forward is going to take 2 times batch and tokens times parameters. That's what the math we were just remembering. But it's going to take 2 times parameters bytes just to load those weights. And if you think about what we remember, the arithmetic intensity is actually 224 in the system. So if you think about how many flops we have compared to how much bandwidth we have, 224 flops per byte. Well, the batch and tokens, if it's one token, they're 2 times parameters flops, but the memory bandwidth is 2 parameters. So we actually aren't going to be able to saturate the matrix multiplication on this chip trying to load the data. So because we're only processing one token at a time. So the kind of the canonical solution here is to process many sequences at once. So the idea is instead of having this chip talk to one customer at a time, it actually talks to 224 customers at a time. So when you're asking one question, someone else is asking another question, and the chip is more efficient at answering both of your questions at the same time than answering any one question at a time. So we always thought that was pretty beautiful. The equivalently, there's attention. And then attention, we read through the key and value cache. So each key and value cache is going to be batch, previous tokens, dump heads, head dim. There's also going to be a number of layers. And if you just multiply that through, it's 939 megabytes per sequence. There's actually basically a negligible number of flops there. So this is always going to be memory bandwidth bound during generate time reading the KV cache. So another quick conversation is how do we think about sharding it? So there's there are always different strategies depending on some really challenging technical details, like mixture of experts, all these things. But the canonical solution is tensor parallelism. So we've seen for training, fully sharded data parallelism tends to be right, and then there's a little bit of tensor parallelism. But for generation, we almost always want tensor parallelism. And the reason to think of it is fully sharded data parallelism requires each chip to load all of the parameters. And we know that won't help for inference because we're already limited by loading all the parameters over from HBM, which is 9.8 terabits per second. So loading the parameters over interchip interconnect can only be slower. So inference is almost always going to be just pure tensor parallelism. And here I've written out the sharding. This is very similar to what we've seen before. Don't mind if not everything here quite makes sense to you, but we're sharding the activations over the tensor dimension. We'll do these as collective map models, which we covered in session 3 or 4. So we'll do each of these 3 as collective map models. So this is going to be projecting from E to F dimension. That's the first matrix multiply. The second matrix multiplies from F back to E. Then we're going to get the Q, K, and V. That's the third collective map model. Then there's actually, now because of the way we sharded things, each chip has a subset of the heads. So it's able to do this operation purely locally. And then the final matrix multiply, the fourth matrix multiply, is also a collective matrix multiply. So again, the generate step is basically 4 of these collective matrix multiplies and an attention step, which can be done all locally for the attention step. Cool. And I just wanted to just like sound this one out for like a real example, so folks can think about the numbers involved. So we've already seen these quantities earlier, but if we just think about Gemma, 7 bits, a very typical model, 7 billion parameters to 14 gigabytes of weights. Each sequence requires 0.94 gigabytes for its KV cache. But the V48, the system I'm running on, only has 128 gigabytes total. So counting that we're using 14 gigabytes for weights, we can only actually fit, even in principle, a batch size of 121 at this 0.94. In practice, we do need to have some margin for error. So we're going to end up with a batch of maybe 110. So that gives us 103 gigabytes in our KV cache, and then 14 gigabytes for the weights. And then we're using 117 gigabytes, and there are going to be 10 gigabytes left over. And none of this is actually going to be flops bound. So we have all these beautiful flops on this chip, but during inference, we actually aren't going to be able to make great use of them, unfortunately. And we're actually just going to, each step will be proportional to how long it takes to load the 117 gigabytes. So just to remind ourselves, doing the matrix multiplies will only be flops bound if our batch is bigger than 224. So in this case, it's going to be 110. So we're going to be memory bound. And then loading the weights is also going to be memory bound. So the amount of time it takes to load the weights is really like 117. We do the step is really like on the order of 117 gigabytes divided by the total memory bandwidth. We'll do a bit worse than that when we implement it, but that'll give us a sense of where we should be able to get to. And then notice by increasing the number of examples, that's actually decreasing the weight we need to load, the total memory we need to load per new token, because we're amortizing down the weights. If we only had to generate 1 token, it would take us about 14 gigabytes to load the weights, 0.94 gigabytes to load the KV cache of that token, 15 gigabytes total. So 15 gigabytes to get 1 token. But here we're getting 110 tokens for 117 gigabytes. So that's obviously better, but we still are extremely memory bound during inference generation, during inference. Cool. Any questions here? There's some more thoughts I have on inference, but I'd love to hear questions. George.
Hey, Rafi. Yeah, really appreciate your lecture. I have a very quick question about the sharding part. So currently, it looks like the sharding is at the number of head dimension. I'm wondering, like, if it's like multi-query attention or it's group query attention, right? Whether if it cannot be sharded at this dimension, we may need to shard at the head dimension, right? So is there any performance comparison or recommendation, like which direct access we should shut off? Oh, sorry, the dimension we should shut off. Yeah.
Very, very good question. So so just to sound out what George is saying, here's a specific example. It's very important. Mine. We'll talk about that in a minute. But generally, what happens if T, the number of tensor parallel replicas, is bigger than the number of heads? And that actually is a little bit annoying. If they're close, one solution you have is actually just to pad it out. So to have some chips not do any work during the KV cache, that does kind of terrible. The canonical alternative is to shard over the batch axis. And that does work pretty well in practice. So sharding over the batch axis is like kind of the canonical strategy as well. And that works well in practice, George.
Yeah, thank you so much. Yeah, thanks.
But you can see that in the efficient inference for Palm paper, which like Rainer Pope wrote, is a very, very good reference there.
Yeah, thank you. I'll read it. Thanks so much.
Great question. Any other questions? Cool. So we're doing some like context for inference that I think is helpful and as the field has changed. So everything I've said so far is like incredibly dogmatic, but there have been a few important changes. So one is we were talking about 1 gigabyte per sequence with sequence length 2048. Nowadays, Google is demonstrating 1 million per sequence, and other companies are up to 120,000, 200,000 even. So that's going to require naively 500 times more memory. There are probably some secret ideas in the field as well, but one of the core ideas is actually this idea called grouped query attention, which George was referencing. So instead of basically having 1 K and V for every Q head, we saw that we were paying a cost for the KV heads that was actually much larger than for the Q heads. We didn't even mention the Q heads. They weren't driving any cost. So the idea is to have this new ratio here, I've called it X, with this grouping factor, where for every group factor of Q heads, we only have 1 KV head. So if that group factor is 1, it's multi-head attention, the thing we already coded. But if the group factor is 8 or 16, we can get a performance improvement proportional to that group factor by having fewer K and V heads. And it really does speed up inference by a great deal, right? So in this case, right, if we got an eighth as big of a KV cache, right, inference would be almost 8 times as fast, like maybe 7 times as fast in this case. But is it actually is the model actually proportionally equally intelligent? So does it converge well? And that's not a question we can answer here, but we do see the field very strongly moving towards grouped query attention to help make inference more efficient and while making a modest trade-off on model intelligence. Another kind of trade-off we can always make is quantization. So we're of course super memory bound. So if we just represent these weights in int 8 instead of in bfloat 16, they could take 7 gigabytes instead of 14 gigabytes. And that's something we're we do all the time for training as well. So we do the matrix multiplies in int 8. So we can also do that during inference. And then the same thing goes for the KV cache. The KV cache, we're able to do it. We can represent the KV cache in int 8, and we get half of the memory bandwidth demand for the KV cache, and that tends to be pretty forgiving. And then there's a third really kind of a canonical idea in the space for getting rid of these big KV caches is like, imagine we just like knew what the next tokens were going to be. So like in this case, so long and thanks for, we knew in advance. That was the prompt. But what if instead we guessed, oh, maybe the answer is going to be all the fish. And then we could put that all through at once. And if that happened to be right, if we could guess what the right answer was going to be in advance, then we could do multiple generate tokens at once. And that would actually help us a great deal here. Unfortunately, Obviously, we can't guess and not necessarily be right, but there's a whole idea of speculatively decoding. So we make a few guesses for the next 2 or 3 tokens, and then we check at the end, were these guesses right? And we just throw away any work that was wrong. But if the neural net would have chosen the token that we speculated into, perfect. We can, in one path, in one generated step, we can get you 2 tokens instead of 1 token. And typically people train a smaller and faster model that very quickly makes the guesses. And then the bigger model runs with those guesses, experiencing a cache hit, if it can. So super important technology, speculative decoding. So next week, we're going to do inference implementation, and hopefully we're going to answer some questions on flash attention. And then also, we're going to look at a good XPROF. Thanks for that question. Cool. That's all I had for today. Anything else on folks' minds? Yes, questions. Love to hear them. Vitaly first.
Yeah, I was thinking since training and inference workloads are different, I think we earlier tried to design a different chip which was actually low in memory for inference, counterintuitive to what we see in KV cache. Like, how do you foresee, like, do we need a different chip design for inference or training, or like, how do you think about that?
So I know about the TPU roadmap, so I just can't say anything about it, but I will speculate on the NVIDIA roadmap, which is very, very beautiful, where they have the H100, which is a good training chip, and they're complementing that with the H200, which is an inference optimized chip. And really the only thing that's changing, I mean, I think it was a very pragmatic choice, is they just, I think, doubled the memory. They 1.5x the memory and 1.5x the memory bandwidth. So NVIDIA is 100% responding to this by doing the obvious thing. So very, very pragmatic decision making.
Okay, thanks.
Great question. Zhang?
Second to last slide, you said the speculative compute was wasted anyways. Can you say more about that? Is that due to the padding tokens being computed anyway?
So you're asking why does the speculative decoding help us?
Oh, I'm asking about the comment in the parentheses. Why was it wasted anyways?
Oh, the work is wasted anyways because we're orphaning the flops. So that's a really good question. I see why that was confusing. The idea is that we, like, imagine we're running with a batch size of like 96. And that means for free, I could do a batch size, because of the arithmetic intensity calculations, I could process 224 tokens. So from my perspective, we're orphaning those flops because we're going to idle them anyway. So if instead of doing 1 token, we do 2 tokens, we're just getting strict 2 for 1. And then if you throw away the work at the end, we've barely paid any cost. So that's the sense in which I meant we're throwing it away anyway. We're throwing away the flops anyway.
Got it. And I guess related to that, in terms of energy use, if you activate those like MXUs, is it much or is it not really?
Yeah, I mean that's a pretty delightful question. It actually is a real amount, but nothing on the scale of like you can see that in the chip. So when we the data centers are tested for like peak load. So if we do that, we have to make high energy use workloads, and those high energy use workloads are higher than inefficient workloads, but it's a very, very modest effect. So it is definitely more energy efficient to do speculative decoding, even if you don't have a very high hit rate, as long as you're getting more throughput. It's a very small correction.
Got it. Thank you.
Great question. Cool. Any more questions? Vitaly?
Yeah, one more question. So I think when we think of disaggregated serving, we essentially separate out like prefill and decode onto different servers, right? But like when I think of a summarization task, typically the prefill length would be much longer than a decode length, right? So can you actually get like higher efficiency on the chip by actually combining the two? So for example, there's some prefill going on, which is more computation intensive, and some decode. So essentially, you might be able to get better out of the chip.
Yeah, that's a really interesting idea. So one of the things Vitaly is commenting, basically, I have prefill and I have generate that have these different computational characteristics. So maybe I should blend them together to find the optimal blend that works for the chip. That's like a very, very beautiful idea. I think it's hard to do in practice, just because it's hard to run these things at the same time because you're SRAM limited anyway. So there's not enough idle, like SRAM, enough for it to be efficient to run the two at the same time on the same chip. A similar idea that's maybe just a tiny bit more pragmatic is that you could run prefill on one generation of chip that has more flops and less memory bandwidth, and you could run generate on another generation of chips that has more memory bandwidth and less flops. So think about like the H100 would be better for prefill and the H200 better than for generate, and that would be another way of dividing the problem to get more efficiency. And I think that one is, people are seriously engaging with that one. Your idea is, I think, very clever, which is very complex to execute.
Cool. Thanks.
Awesome. Cool. Any more questions? Great chatting, folks. Have a good rest of your week. Talk to everyone next week.